Okay, Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. Let's get started. You had some questions about the assignment. Basically, we're going to start by discussing your questions about the assignment number 1, and then we're going to have some more experiments. Just review what we did before on baseline wonder artifact. We're going to try different kinds of filters, FIR, IIR, and frequency domain filters. We're going to talk about quantitative estimation of performance and the practical issues involved in that, such as the transient, the gain, the DC shift, the reference, etc. We're going to talk about the other 2 types of artifacts, which are the muscle artifact, the EMG artifact, and the electrode motion artifact. And we're going to find out that the problem in such cases will not be as easy as a problem with baseline wonder. And finally, we're going to talk about how to report the results in a scientific paper form, which is going to be a requirement for each one of the research problems that we're going to have this term. Okay, so let's get started with your questions. Please go ahead with your questions.
About question 1 for simulate signal.
Okay, you see the question now, right? Which part?
About all signals, 3 signals that the first one 30 hertz with amplitude 100. We did it little steps. We didn't know it is correct way or not.
In which part? What was confusing to you? Which part was confusing to you?
The zero phase filter. It is only put flip on the signals. That's it.
That's it. It's very, very simple, right? Instead of just using filter, just use filt. That's it.
Because exactly I did it. I didn't correct way.
Don't worry about it. Just do, what you understood from the question, and if there is anything that is different from what I wanted, I will let you do that. I will basically comment on it and let you basically resubmit it, and I will accept it. Okay, the assignments are not like the assignments in the undergraduate where you're supposed to get a particular model answer. No, it's like that. So basically, if your answer is not is different from you understood something different from what I wanted, I will let you know and basically let you change or modify what you submitted, and it should be fine. So don't worry about that. Just do it based on what you understood from the question. Okay?
Okay, you need code, right?
Yes. Basically, the assignment should be submitted as one file, one M file. That's it. Okay? And basically, in each one of the parts, you basically write the documentation. Just write, for example, this is part 1.1. This is part 1.2. Just put a comment with the question that you're trying to answer. That's it. And if there is, for example, such parts as comparison, okay, if you want to basically compare the different filters in terms of, don't worry about in terms of, just compare them, okay? And basically, just comparison and write the comparison as a comment inside the file, okay?
Okay, that means the question 1. There is 1.1 code and 1.2 code. There is 4 codes.
Just put them basically in one code. Basically, you have the part 1.1, then 1.2, and 1.3, and so on for the other questions also inside the same file. So when I run the file, I should see the results for all parts, one by one. So the first, then the 1.1, then 1.2, then 1.3. Basically, I just want to have a sequential codes for each one of the parts that I have in the assignment. Is that clear, or you still have any questions?
I have a question, doctor, about the I successfully do the zero phase filters with the finite impulse response FIR, but uh, in the IIR, when I use field, the signal becoming all zero. It's not
There must be something wrong with the filter. So basically, did you use the right filter? Did you use the right specifications for the filter?
Yeah, I did like in the first in the filter designer, and then copy the code.
So filter works without filter. If you use just filter.
Yeah, if I just filter, then it works. The IIR works, but if I change to the field, the result is becoming zero. I'm not
It's
sure.
kind of strange, but you might want to change
Yes,
the design of the filter.
become like a straight.
Okay, you might want to send me that, and I'll look into it. Don't worry about it. Just
Okay.
basically, if you use the right function like filt, and you got a result that you didn't expect, just put a comment on that, and that's it. You don't really need to do anything more than that. Okay.
Okay, doctor. As my friend Reno said, when you made or make flit, it's become zero, straight one. Okay, we will be comment that. But now, and my question exactly, we need array. It's you need in the result. There is many signals. First,
just plot them. Basically, I expect you to plot them to show me that you got the right result. Okay, so basically, when you say, for example, for part 1.2, you should retrieve the 100 hertz component only. Basically, should show me the input signal and the output signal in one figure. Basically, like what we did before, you have you can have subplot, and the first one should have the mixed signal, and the second one should have the output signal. Okay, or you can choose to have just one figure for problem 1, with the first one having the mixed signal, the second having the answer to 1.1. You put the title 1.1, the third will be 1.2, the fourth will be 1.3. Okay. Or basically, you can just for each one of these parts, you can have basically all the figures for the 3 filters that I'm asking for in one plot. Just basically in one of the just an array of figures like subplot 4 by 1. Okay, so basically you have the original signal and each one of the filters, the 3 filters, in a figure, in a different figure. So basically, the answer to your question is that I want the answer in a graphical form, in a plot. I want to see the output as a plot, okay, so that I can verify that it came out correctly. That's it. Any questions in that part?
No, sir. What about the deadline for that? Because sir, we have work. And
that's fine. That's fine. When
all
will
Friday, doctor, the cases in the hospitals, it's become increased in these days.
No problem. No problem. When would it be suitable for you?
Okay.
When would you like to have the deadline moved? What would be the suitable deadline for you?
Because doctor, we exactly started, most of us, yesterday at night, because there is work Thursday.
No problem, no problem. I'm just asking you if you want to change the deadline. When would be suitable for you? When would be the suitable deadline that would basically allow you to finish the different parts of this assignment?
Okay. My discuss with us about this.
So you're going to discuss it with each other and then let me know?
Yeah, please.
That's fine. By the way, the assignment as it is on Blackboard, you can still submit after the deadline. It's going to tell you that it's late, but it's fine. I'm not going to have a late deduction or anything like that. So basically, there is no penalty for submitting late. So you can submit as late as you want, and it would be acceptable, okay? So don't worry about the deadline. Just submit whenever you're ready, okay? Any other questions in the other parts? Any things that might be confusing to you?
If there's anything about the second problem and third problem, will be told you, sir, in WhatsApp, if you don't mind.
Okay, that's fine. That's fine. But I mean, it's you haven't started on question 2 or problem 2 or problem 3?
Not yet, because we exactly saw the first one. It is the a lot of question in that one.
Okay, but after the first one, basically the second and third ones shouldn't really be as difficult. But
Yeah,
that's fine. That's fine. So should we get started now on the topics?
Okay, sir. About the second and third and the first one also. It is only from 3 lectures, right?
Yes. Yes. Yes.
This about today lectures. It is not with that assignment.
The first part of today's lecture will be a review of what we did before. So it will be basically a review of what was supposed to be done here.
Okay.
So basically, I'm going to go over things that related to problem 2 and problem 3 before I go to another additional part. Okay, so basically there will be a review of what you will be doing on problem 2 and problem 3 today. But these parts are review from last time. Okay, they are not new things. The things that are new basically will start with the quantitative estimation of performance. The one before that, if you see the content, basically more experiments on baseline Wonder artifact filters, basically just going to be basically reviewing all the techniques that we use so far. So we're going to start with that, and basically this is very much related to this question here. You're going to start with ECG signal with baseline Wonder noise and sampling rates. Basically, this is exactly the same signal that we have. And you design and optimize the performance of 3 different digital filters that would remove the baseline Wonder noise without affecting the true ECG signal. Okay, what I'm going to do is just try one filter from each type. In order for you to optimize, you just want to change a few parameters. I'll show you how to optimize, but I'm not going to do the optimize, leave the optimization for you. But actually, we're going to do this part, a similar thing to this part right now. Okay? Then we're going to do the frequency domain part also after that. Okay? It's a review to that. Okay? So here, basically, you're going to provide the filter order, the group delay in passband, the transient duration in seconds. Basically, I'm going to show you how to get these parameters for each one of the solutions that we're going to come up with. Okay, so here, just imagine that I'm going to solve problem 2 for you now. Okay, this is the first part of this lecture, just solving problem 2. Okay, so what we're going to do, basically starting from the ECG signal with baseline Wonder, basically when I tell you this, all you have to do is just go back. Remember the demo code that I gave you, ECG demo? I'm going to start with that, okay? As we did every time, basically. This is ECG demo, okay? And then I'm going to save it, save as, demo, let's say problem 2, okay? Start with it. This is basically the code that we use to just read the two files that have the data and just display the signals, okay? I'll just run it now. Basically, you have all kinds of problems basically displayed in front of you, okay? What I'm going to do now is just select the part with the baseline wonder, okay? This is actually, this is the EMG noise. So basically, we want to have something that looks like this, basically. You have two signals, by the way, S118 and S119. These are from different patients. And basically, I'm going to, maybe I can just take this one, the one that we saw before. This is in figure 3. So basically, I'm going to cancel out or basically comment. Maybe I can just remove them all or just comment them so that you know that we commented them, okay? Okay, so I'm just going to comment all the parts. Here, this part, the signal where you have the baseline wonder, okay, is right there. So basically, if I just say close all here also, we're gonna close all the figures, and here I'm using S118. So basically, I don't need to load that one here. So basically, I'm just gonna run that so that's what's gonna happen. It's gonna close every figure. Basically, this is the signal I have right now. Basically, I have the original, I have the baseline wonder signal, I have the artifact. Okay, this is the signal I'm going to start with. Okay, so basically the signal here, the signal I have here is what I should start with. Basically, I should have a range for the signal because the length of S118 BW12, if you go to MATLAB, the length of, actually the length is 10,000, it's fine. But actually it has two signals. Each one has two signals. If you see here, it has two signals. So basically this one has two signals, this one has two signals. I need only one. So basically what I should do is basically instead of saying this, I'm just gonna say this is equal to whatever here, whatever I have here, so that it's clear. Okay. Let's put these up there. Okay. And sig noise is equal to the same thing here. So that it becomes a little bit clearer. This is here sig, which is the true signal. Sig n is the one with the noise. Okay, and here I'm going to have, instead of this, I'm going to have sig n minus sig. Okay, so this is the difference between the one with the noise and the noise. Okay, I did it this way so that I can have a signal. Basically, the original signal is in sig and the noisy signal is in sig n. Okay, there's a problem here. One of the. Oh yes, that's true. This is another one.
One down.
Okay. Okay, here. Okay, so these are basically the things that I have here, okay? What I'm going to do now is basically, since I have here my signals, okay, these I'm going to use basically to apply the filter that I'm going to design, okay? So I'm going to copy this part, basically the part from loads until this part here. And basically this will allow me to get started on the filtration when I have the filter ready. Okay, but now I have the original signal and the noisy signal. Okay, So whenever I start with, if I wanted to start with baseline wonder, I will do this. If I wanted to start with electrode motion, I will do this. I'll take these signals. If I wanted the EMG, the muscle artifact, I will take this one here. Okay, so basically, actually, the easiest thing to do is just change this. So for example, if I change this to motion artifact, oh sorry, muscle artifact, it will give me the signal with the muscle artifact. See now, this is the different type. So when we try the muscle artifact, we're just going to replace BW with MA. Or we can also replace it here by EM, electrode motion. And it's going to give you the other type. Okay, so let's keep that. Okay, and just maybe you can just take this part down so that we can have the important part up. And I think the figure here is not that important, so I'll just take it here. Okay, so that whenever I want to have the signal for one of the types, I will just copy this part only. Okay, so we'll leave it at that. Okay, here. What I'm going to do now is let's run it with the baseline wonder. Okay, this is the artifact that we'd like to remove. As we said before, we have to get an estimate of, first of all, the type of filter we need, and second, the specifications of this filter. Okay, so basically, as a start, we see that the variations in the artifact are much slower than the variations in the ECG. See here how many periods of ECG in each one of the periods of the artifact. So definitely the artifact is low pass, is low frequency. So apparently when we have a noise that is low frequency, we will need a high pass filter to be able to filter it out. Okay, so which frequency? What we said last time is basically we should basically get an estimate of this artifact frequency. Maybe we can just consider it as a sinusoidal signal, so we can measure the difference between two peaks or two valleys here and get an estimate of how much frequency is there. So basically, how much is this point? Basically, this point here, you can just stand here. I will give you frequency. Which frequency? Frequency is what? 3798. It's about 3800. Okay. How about here? It's about maybe 6400. Okay. So 3800 and 6400. So if we go to the this part here, we'll talk about this later. Basically, we have the first point, basically, okay, this point here is at 3800. And this point here is about 6400. As you saw, I'm not really trying to be really accurate in the measurement, because actually what we're trying to do is a rough estimate. And we know that this is a rough estimate. This will never be exact, okay? So I just got rough estimates, okay? 3800 and 6400. What's the difference between these two? Difference is what? 14. First of all, 0, 0. 14 minus 8. 16. 6. And then 5. 600. Right? Okay. These are points. Or samples. Maybe you should write it with the correct terminology. It's samples. Okay. You would like to have that in seconds. How can we do that? Basically, we're talking about samples. Okay. These are 2600 samples. Okay, in order for us to know that in time, in units of absolute time, we need to know exactly how much is the sampling period is, right? we know that the sampling frequency is 360 samples per second. So TS is what? TS is what? 1 over Fs.
1 over Fs.
Which is 1 over 360. So basically, this is in seconds. So in order for us to convert that to seconds, it's 2600 times 1 over 360. Basically, it's seconds per sample. So when we multiply sample times seconds per sample, basically it's going to be seconds. So how much is that? Let's get another rough estimate. We are too lazy to use a calculator, okay? It's too lazy. I'm just trying to show you how engineers work, okay? So basically, just make this 3, okay? So yeah. 2600 over 360 is going to be what? Going to be 10 seconds, right?
Yeah, 10 seconds.
Which is what basically amounts to a frequency of what? If this is the period of the noise, then the frequency of the noise is what? 1 over 10 hertz. This is a very rough estimate, but actually we're going to accept that. Okay, so basically we're going to start with assuming that we have a frequency of the artifact around 0.1 hertz. So what I'm trying to do now, what I'll try to do now is just use filter designer. Okay, the one that we used before, and try to make sure that that 0.1 hertz is basically in the stop band. We said that basically let's show the filter that we actually decided that we will use. It's a high-pass filter. High-pass filter looks like this. It basically starts from a certain frequency. You have a pass band frequency here. It passes all frequencies above that, and basically it attenuates the frequencies below that. But we have to distinguish between 2 frequencies, the pass band and the stop band frequency. The stop band frequency will be guaranteed to have at least a certain amount of attenuation. So you can say that all the frequencies below the stop band will have an attenuation of 1 over 1000. It's going to be attenuated by a factor of 1000. If the amplitude is 1 coming in, it's going to come out as 1 over 1000. Okay? The problem with the Fpass is that the Fpass is a 3 decibel bandwidth, basically, is a 3 decibel point, meaning that the attenuation is 3 decibels, or basically 1 over the square root of 2. Okay? Basically, basically this is just the border of the pass band. Basically, the border of the pass band is close to passing, not close to stopping. So basically, I have to choose a particular frequency that would be guaranteed. Basically, the curve will go like this. Basically, it's going to go down starting at Fpass. I want to see when it will reach the attenuation that I want, okay, and call that stop. I design my filter. One of the design specifications of my filter will be that f-stop and that attenuation that I'm going to choose. The closer f-stop to f-pass, the much higher the order will be. Okay. The same thing if you choose the a-stop as really large number that is not necessary, it's going to also basically make the order very high, extremely high. Okay, so basically, first of all, we start with putting the correct f sampling for the signal here. And the f-stop and f-pass I have to choose here. I want to make sure that 0.1 hertz is inside the stop band. So meaning that f.1 should be somewhere here. Okay, it doesn't have to be the f-stop. Okay, I can make it the f-stop. Maybe I can try with that. Okay, I can make that 0.1 here. That's fine. I can try that. Okay, and I can make the f-pass anything above that. So basically, if I'm not worried about the ECG, and if I'm sure that my signal doesn't have very low frequencies, I can maybe choose that as 1. The advantage of using that as 1 instead of 0.5 is that basically the transition region here between the f-pass and the f-stop will be a little bit wider. The wider this becomes, the smaller the order of the filter will be. We will try that now, okay? Here for the f-stop, we said that we can put it in units of decibel, where each 20 decibels will correspond to 1/10. Okay, so 80 decibels, it's 4 times that. It means that it's 1/10 to the power 4. Okay, each 20 decibels is a factor of 1/10. So basically 60 decibels will be 1/1000. 80 decibels will be 1/10,000. 40 decibels will be 1/100. Okay, so maybe you can just try to relax that a little bit. Maybe you can put it as 40. Okay, 40 means that it's gonna be, the noise will be divided by 1/100. It will be divided by 100 basically. Let's try to design the filter. Okay, it looks like this. Okay, it seems okay. Basically, it's very difficult to see the parts here, of course, because it's a very narrow bandwidth here. It's you have only 1 hertz here, so basically it's very difficult to see this region. But the order apparently is very high. The order here is about it's about 600, but it's fine. Let's try that. Okay, so we're going to do like what we did before. I'm going to get the filter design function. I'm going to call it Highpass Filter. Okay, lecture 4, Highpass Filter 1, FIR. Maybe I should put FIR here, FIR, because it shows FIR filter, Highpass Filter 1. Okay. As we said we will do before, I'm just going to comment out function. I think you probably did that in problem 1. And here I have the filter here in HD. I'm going to copy the part that I said I will copy from here. This is the part where I have the signals. I'm going to place it here. Okay. So now I would like to have SIG-F, the filtered version of the signal. It's going to be what? Filter of SIG-N, and I think it's HD and SIG-N. I'm not sure. It's very difficult for me to remember the functions actually. So I have to keep, it's HD, comma, SIG-N. Okay. So I'm going to try to plot this filter, this filtered signal. So basically I'm going to have figure 1. And maybe I can copy it from somewhere where we tried that, so that it comes exactly the same. Actually, it's fine. I'll just try it here. Subplot, maybe 3, 1, 1. Plot of sig. I'm just going to plot the signal first, and the title. Original. This is SIG-N and this is SIG-F. This is and this is filters. Okay, let's try that. Okay, how do you like the result? Does it look okay?
It does look okay.
Looks okay. Okay, we'll try that with the filts. So we're gonna have, let's call it sig FF. Filt of H. Oh, okay, we have to, I think we have to basically get the components transfer function, right? This is what we did before. Basically, before we did the filt here, we have to get the transfer function of the original filter, I think. Where? Of this one. I think it's somewhere here. Yes. Yes, we have to do that. Basically, filt doesn't use the complex form of HD. So basically, I'll put it here so that it's clear. B and A, B, comma A, comma Cn. And we're going to have another figure here. Add another figure. And write zero phase filtered. Sig FF. Okay. Okay. 4. Is there anything missing here? Yes, it's right there. Okay. So basically it looks exactly the same. It's actually better than the first one because actually see here some variations. They are not present here. And these are among the things that we're going to talk about when we try to optimize the quantitative measures of performance. So actually it should work like this. The optimization part, this is an FIR filter, okay? Basically, you can change these parameters and try to see how much that changes the filter itself. So basically, first of all, the transient part, basically the first part here that shows transient before the signal stabilizes. This is basically, as we said before, this is the order over 2. You have basically, if you have an order of 600 like this one here, you will have 300 points where you have transient. Okay, so this is one of the parts that you need to have for your assignment here. Basically, the transient duration here is basically related to the order. Okay, but actually here I'm talking about if you have an order of 600, you have 300 points or 300 samples of transient. You have to change that to seconds. What would you do to change it to seconds?
1 over.
Yes, multiply by 1 over 360, right? Let's do that right now. Basically, you need here the filter order. Filter order actually comes directly from the design procedure here. This is the N, okay? This is the N that you have here, okay? So basically what I can do is, I can, first of all, whenever something comes up, I will just display it, okay? So maybe I can just do it right now. So basically, I can say that this filter order, and maybe I can just have it like this. Filter order. Then I'll just write N, basically, that's it. Or display N. Okay. And if I wanted to have the delay for the transient duration in seconds, basically is going to be basically N over 2 times what? Basically, you have the frequency, Fs is the frequency, the sampling frequency. So basically, I can just have it over Fs, right? Because it's multiplied by 1 over Fs. Okay, let's see that. The filter order is this value here. The transient duration is this in seconds. Very simple, right? How about the group delay? How about the group delay in the pass band? Okay, let's go back to the filter designer. As we said before, you have different options here to display. Basically, some of them will display the phase response, some of them will display the group delay response, which is minus d phi by d omega, okay? Basically, you'll see it like this. How much is that? Is it related to the order? As you said before, in the FIR filter, it is related. And it is exactly equal to basically the order over 2. Okay, so basically for the FIR filter, if I have an FIR filter like this, I can basically have another one of these and say that basically the filter group delay is equal to n over 2. That's it. The group delay, you can display it in seconds or in samples. Usually the group delay, as you see here in the figure in Filter Designer, usually in samples. It's given in samples, okay? So basically you just give it in samples as the order over 2. This is very specific to FIR filters, okay? So basically with this here, if you run this function here, basically you'll get the results that you need for one experiment for a filter. Would that be enough? No, this is one experiment. You need to optimize that, okay? How to optimize that? Just play with these parameters, okay? Just play with the parameters that you see here, okay? For example, maybe I can just, instead of having D stop as not D stop, the F stop, instead of 0.1, I can just have it 5.5. Let's try if that makes a difference. Did that make a difference? Let's see. The order now is over 1,000, so it's not good. Because basically, imagine that what we did is make the order, make the F pass and F stop closer. But actually, I can change the F pass to be 2 seconds, 2 hertz. So that it becomes a little bit less stringent. So basically, is the result still okay? Is the result still okay, or do you see any problems in the results? It seems to be kind of okay. Let's see the order here. The order is less. The order is still 600. I have it now like 350. So this is a little bit better, okay? So basically what you need to do is just do some experiments, just do some changes and see the outcome, how the outcome will be, okay? Just do some changes here in the parameters here and basically try to see if this will make a difference or not. Maybe I can do something a little bit more. So basically instead of this top here being 0.01, I'm just gonna make it 0.1. So this is less has less variations. It had more variations actually. Okay, so obviously here the transient time becomes smaller. So here the order is 200, almost 200. This is better. So this is a kind of optimization I expect you to do. Okay, just vary these things and see which one will give you a better result. Another kind of variation you can do is if you go back to the filter designer, basically when you choose to design the filter as FIR, you have several options here, not just one option. Try these, okay? Let's try one of them. Let's try, for example, window, okay, and see if it makes a difference or not, okay? So the window here is Kaiser, okay? And it's exactly the same parameters that we started with. Let's try to see if this will give us a better option or not. Maybe you can try that optimization here first until you get something that would look good, and then go back with it and try it in basically optimize a little bit further with the actual signal. So here the order is about 900, which is really large. So this doesn't seem to be a good way of designing that. Let's try to have interpolated FYR, for example. Okay, let's try that. Okay, it changes everything here, sorry. Have to change the, make sure that the parameters are still there. 0.1. This is 1. This is 40. Let's try that. It's still very high, 650. So basically, one of the optimization that you can try first, you can try one of these first, okay? And then after you get an acceptable result here, or a seemingly good result here, you can take it and do some further optimization with these parameters on the signal itself. So for that one here, it's about 400, which is okay. It seems okay. So this one should be okay. Same thing you can do with IIR filters, okay? You can also choose different filters. You have different types here. You can choose one of them and basically proceed to try and see if it works or not. Let's try that now. So do you know how to do that for the FIR? Do you know how to optimize for the FIR? You can optimize these parameters. Basically the f-stop, the f-pass, the d-stop, the d-pass. Basically, these are the parameters that are here. This one, this one, this one, and that one. You don't change the sampling frequency. You never do that. If you change the sampling frequency, you're designing a different filter for a different application. So it's not going to work. You change everything except for the sampling frequency. Okay? So basically, you choose one of these techniques for the design. And then when you see that the order is okay, or the lowest that you can get, you can generate the filter design function and then proceed to change these parameters. Basically try different options here and see the result, whether the result looks okay or not. So do you have any questions for the FIR filter? Any question about how to optimize an FIR filter?
So it started from the filter designer, isn't it? Okay. So
you design the filter specifications that you started with, okay? And then you change, you can use one of different ones here until you get something that looks okay. And then you generate the filter design function and you optimize a little bit more by changing those. The thing is, these are, the changes in these depend on the signal you have. Okay, so basically if you change the f-stop, for example, you want to have your signal, you want to have the output, you want to have this figure in order for you to see if it works or not. Because, for example, I can choose here, in this one here, I can choose f-pass as 10. Okay, if I choose it as 10, basically the order comes out like 32. It's 32. So imagine that you had a filtered, basically the filter order was originally 600. Now we have 32. Is the result acceptable? No, it is not. See? So basically the changes in the f-pass, f-stop, attenuation pass, attenuation stop will basically have to be done with the signal output, you know, on display, so that you can judge for yourself if this is acceptable or not. Because basically the specifications we started with are not exact. Since they are not exact, we're trying to optimize in order for us to get close to the exact specification that would work for our signal. Okay, so without having the output, we will not be able to do that. Is it okay? Is it clear?
Okay, Doctor, it's clear.
Okay, so let's try the same example with the IIR. So we'll go to the filter designer and choose IIR. Let's choose one of the others here. Let's choose, for example, elliptic function, whatever. Okay, This is 360.11. Just make sure before you design, just make sure that the parameters are okay. So we design the filter. Okay. It looks a little bit strange actually because the order is 2. Okay, it doesn't make sense, right? It's not really realistic to expect it to be like this, but actually the specifications, the filter response actually doesn't look right. Basically, you have the group. This is the group delay. I'm sorry. Let's look at them. Actually, the response looks okay, and this is an order of 2, which is okay. Let's try that. Let's try to see if it works or not. Filter design function. Leg 4 IIR HPF1. Right there. I'm going to do exactly like I did before. Just going to comment out that. I'm going to take the whole part, basically the port after the end of file here, and just put it here in the other file. We have to notice something. The part about the group delay here will not be correct. So basically I have to comment that out. Why? Because basically if you go to the filter designer and look at the phase response here, it doesn't look linear. Okay, the group delay here is very different in the pass band. This is supposed to be the pass band here. It's actually not very clear. I'm not sure exactly how much is that. This is almost 0, but actually it's very strange because here basically this part, this is a part of the pass band, because actually the pass band starts from 1 Hertz. So you have variations here. This is 1 Hertz, about 120 samples in group delay. Okay, and if you are about 10 Hertz, you have almost 0 group delay, which doesn't make sense. You have a lot of variation. So for the IIR, the group delay will not be as easy to compute. So basically, we're just going to have to say that for IIR, we do not have, basically, it ranges from 120 to 0. Okay? So it's a range, it's not a value. So basically here, that's why we're not going to be able to basically print it out like what we did in the other one. For the transient is almost going to be 0. Let's try to see what the output here looks like. Actually, it looks very good. It looks extremely good, actually. If you look at this here, it looks almost exactly the same, or basically much better than here. So it looks very good, actually, for the 0 phase filtered signal. Here, because you have the transient here, basically you have this one here up, basically at 600. So basically this one here looks a little bit compressed, but actually it looks like this. If you just take it in the right range, it would look like this, basically. So basically here, let's see the output here. The filter order here is 32. 32 is it 32? Actually, it looks like 2, but I'm not sure exactly why it says it's 32. Oh, okay, I understand now. Here, because the design here doesn't have the order of the filter doesn't appear here. So also this one will not work. Okay. So basically, we will have to see the transient also, because it's dependent on the order. We have to actually measure it. We have to look at the filter response here, this part here, and basically detect the effective order based on basically in the transient period that we see here. So the order of the filter doesn't really appear here. There's a function that allows you to do that for the IIR filters, but actually I don't remember it now. But actually I'll send it to you. But actually it's you can just get the order from the filter designer. Okay, you can get the filter designer. You can get the order from here, and basically, for example, if I change this to 0.5. and design the filter again, basically can get the order here from this and basically use it as a result of this part. So the optimization here, of course, if it looks like this, the optimization is not really needed, but actually you can still optimize by changing those and by going back to the filter designer and changing the type of filter. So let's try to, for example, Butterworth. So the Butterworth, the order is 3, which is really amazing, actually. All these are really very low orders. If we choose Chevy Chev, still 2. Okay. So basically, the orders are really low for this particular type, for the IIR filters. But basically, you just report it from here. If I increase the attenuation a little bit more, like 60 or something, probably the order will be a little bit higher. Not much higher, actually. So the filter response will still be okay. It's about 3. It's just nothing really. Okay. So basically for the IIR, it should work. It's apparently working here. Okay. Just report that. You report different types. If you try a few times, you really don't have to try 10 times, for example. No, you really don't need to do that. Just try that 1 or 2 times, and that's it. Just try maybe changing the values 2 times, and that's it. Okay, and just choose the one that you think is okay and basically report it. I would like to see you try that optimization procedure. That's it. I don't want you to do the optimization, over a day or something. No, it's not like that. Okay, just show me that optimizing the right way by changing which parameters or using which technique for the design here to be able to optimize the filter, and that's it. Is that clear?
Yes, Prof.
Okay, sir.
Okay, so this is for the IIR filter. So do you have any problem with the IIR filter optimization? Again, we're going to start with the basically type of filter we want, put the parameters, and then choose different types here until we get a type that looks okay, that looks basically like it's giving us the best performance in terms of the order. And then generate the filter design function, and then go to the filter design function and see the performance, make sure that it works, and then tweak the values for the f-stop, f-pass, a-stop, a-pass, and basically until you get something that would look as good, but with less order. Okay? So basically, we have the highest priority for the optimization. Maybe you can just write that down, just to be sure that we all on the same page. We're all on the same page. So filter optimization. So basically, there are parts that are fixed, which are the F sampling, and the basic specification, or basic at least F sampling. Maybe you can just forget about the basically. This is the only one that is really needs to be fixed. Okay, F sampling needs to be fixed. We start initial values, initial estimates for the parameters. Okay, F pass, F stop. And basically choose A pass and A stop, the attenuations for the A pass and A stop, basically as reasonable values. So these are rough estimates from noise, characteristics. Okay, and basically these actually usually you would say that basically the A pass you can just leave it as it is. The A stop you can choose attenuation of 1/100, which is 40 decibel, or 60. Okay. Then the optimization, the actual optimization, or basically the start optimization in Filter Designer, basically the technique. In the Filter Designer, you have for FIR, for IIR, you have a menu with different options. Okay, so what you do is basically say that I'm going to choose, or I'm going to try this one, this one, and this one. And from these two, actually, this one gave me the best result, so I'll take that one. Or here, I'm going to try also 3 options. This one came out as the best result, so I'll take this one. Once you do that, you generate the filter design function. And basically, once you generate the filter design function, the rest of the optimization you have to do it while applying to signal. So the first part here, you really don't need to do that. Okay, so basically for these parts here, the selections here, you can do them, or at least the part for the technique here, you can do that without looking at the signal output. Okay, for this part, once you generate the filter design function, optimize these parameters, these 4 parameters, while applying to the signal. You just see that, try to make the or transition region a little bit wider, try to make the constraints a little bit less. For example, the attenuation, you want to have a less attenuation in the stop band, for example, to try to make the order a little bit less. And basically your target is to make the order as small as possible with the same performance, or with acceptable performance. Okay, you don't want to change the order to be very small and sacrifice the performance. So basically, the highest priority, the priority here is the performance, meaning that get the job done. Okay. Number 2, lower the cost, which is basically the order. Mainly everything is related to the order, the cost of the implementation of the filter, whether it's analog or digital or anything like that, and also the associated things like the transient duration and the group delay, things of that sort, are all related to the order. So basically you need to have a lower cost by lowering the order. But actually, if you don't meet that, this doesn't make any sense. Okay, this is the most important. You have to satisfy the first one. If you don't satisfy the first one, everything else will be meaningless. Okay, so the performance is your highest priority. You cannot have a lower performance. You cannot have further artifacts in the signal or remaining artifacts in the signal, okay, while having a lower cost and say that this is good. No, this will not work. The optimization does not sacrifice the performance. It basically gets you to a point where it's acceptable. It's not perfect, but it's acceptable, okay? So basically, if it's below that, if it's below acceptable, then it's unacceptable, regardless of how the order will be. Is that clear? So do you know how to apply that?
Yes, doctor. It's clear.
Okay. So basically, this is what you should do here. This is problem number 2. You're going to do that. Okay. So this is what you will actually be doing here. The third type of filter, we can do it with the Fourier transform filters. Okay. The Fourier transform filters is what we did last time. It's basically we just create an ideal filter. Okay. So let's discuss it here first and then go back. Just review it here first and then go back and implement it. So basically what we said before, the meaning of filter is that it's frequency selective. Frequency selective behavior. Okay, meaning that if you have a frequency domain, for example, if you have a frequency response that would look like, for example, this is your signal here. Okay. By the way, if you have a real signal, and this is the frequency domain, okay, this is 0, this is positive, and this is negative. Okay, a frequency domain of a signal like this, basically of f or of omega or whatever, it has to be symmetric. If it's a real signal, it will go to frequency domain as a symmetric signal. The frequency selective behavior means that basically I say that I accept these frequencies, or this range of frequencies is acceptable, and this range is not. Meaning that I have basically I created a function that would basically treat the different frequencies differently. So I have h of omega or h of f or whatever, h of omega. At each frequency, it will have a different value. So I can have, for example, these frequencies multiplied by a value that's very small, and these frequencies multiplied by a value that is almost 1. So this means that the outcome of this will be basically the frequencies here only, and the other frequencies will be very much suppressed. Okay, so the idea of frequency domain filters, that the thing that we talked about last time, the frequency domain is like this, basically. I have a block, just take the signal, measure this is S of t. I'll take it to a block that performs frequency domain. This is Fourier transform. Okay, this will come out like S of omega. Okay, what I'm going to do is take that and multiply it by h of omega. And basically, the outcome here will be S filtered of omega. All I have to do is go back. Okay, so basically I take the frequency domain, or basically take the signal, the original signal, and transform it into the frequency domain. And then basically the frequencies I don't like, I remove. The frequencies I like, I keep, and that's it. I can go back. Okay, so for example, the thing that we saw last time, maybe we can just go back and run the same code that we talked about last time. Basically, this is the code that we generated last time. Okay. Basically, here, this is This is the actual. Actually, it's not very clear. Maybe you can just. It's very difficult to see here, actually. Okay, that's fine. So I'll just explain it. So basically, if I have my signal, the signal I was talking about now, basically I expect the noise to be low frequency. Okay, so basically if I take S of t and S of omega look like this, something that looks like this. Okay, it has some interesting parts here. As I said, it's going to be symmetric, and I have a signal, a strange signal here that's not supposed to be there. I don't really expect the actual signal to have low frequencies this way. All I have to do is come up with a filter that looks like this. It's 1 here, it's 0 here, and that's it. Multiply the filter here with the original signal here, so that this part will be just gone. Will be multiplied by 0, it's gone. So basically this is an ideal filter, because basically it's not going to be like the filters that we saw in Filter Designer. Let's go back to the Filter Designer and see how the filters look like, just for you to remember how it looks like. Basically, maybe I can try a low-pass filter so that you can see it a little bit clearly. Just any filter, it doesn't have to be a filter that we want. See, this filter is what we get from FIR filters. Basically, it's not ideal. This is the frequency domain. Here, this is the part of the pass band. This is the part of the stop band. You see so many variations. In the frequency domain, this is not the case. It's either there or not there, meaning that it's multiplied by exactly 1 or multiplied by exactly 0. So this means that the pass band here would look like a constant, okay, here, and the stop band would be basically 0 here. That's it. And here we don't really care about the transition region, actually. We just talk about pass or not pass. That's it. We don't have F pass and F stop in the frequency domain. So you can have an ideal filter here where basically, for example, this value here can be basically at, say, 1 hertz, it would pass, and 0.999 not pass. Okay? So basically, if it's there or higher, it's okay. So here or lower, it's gone. You can have a transition region that is really very small. Okay? All we have to do is just get the frequency domain, look at the frequencies that we don't like, and make them 0, and that's it. Go back. Okay? This is what we did last time. Okay? If you remember from what we talked about last time, if you have, basically, if you imagine that we have a signal that has samples here, try the